So today I'll talk about the digital Bitbox, a hardware wallet. Is everyone familiar with the general concept of a hardware wallet? Anyone not familiar with it? Okay, so I'll explain a few details. I think most of you are familiar with Bitcoin, so I won't go into that into too much detail. Of course, it has a lot of interesting advantages. One that I personally like a lot is you can be your own bank. So you gain privacy. There's no middlemen to take away money when you want to use your coins or when you want to hold your coins, and so on and so on. Avoid governments from seizing your accounts and so on. So being your own bank, that's a lot of power, and with power comes responsibility. And if you are your own bank, then you also need to be your own security staff in your own vault also. And this, especially for non-technical people, can be quite intimidating. And even for technical people, it can be quite complicated to do it correctly. And so what do people normally do? Well, one option is an online wallet, which means trust someone else to be safe for you. And of course, there's lots of examples throughout the recent history of this not being so safe, with large failures at wallet companies or exchanges if you have your money on exchange accounts. And the general idea is if you don't own your private key, you don't own your Bitcoin. So how do you own your private key? One way is with software wallets, where you download software onto your computer or your smartphone. But these can be susceptible to malware, keyloggers and so on, stealing your secrets. Paper wallets and cold storage, this is probably the best way to be safe. And what this means is basically you just have your private keys on a piece of paper or some technology that never touches the internet. And hardware wallets are basically a way to make cold storage simple, easy to use. And so it combines the benefits of cold storage, where your private keys are never touching the internet, for example. Yeah, no problem. And it combines this security with the convenience of software wallets. So you can use software wallets as a front end to interact with the hardware wallets. This is a hardware wallet, the digital Bitbox. Looks like this. It's one piece. There's no battery chargers, no cables. This is all you need. It comes in a sturdy case filled with epoxy. Has a touch button for user confirmation that has a LED as a backlit. And it accepts a micro SD card that slides in like that. And the micro SD card allows for secure offline backups. So you can make backups, and your backups never have to touch the internet also. And so the digital Bitbox goal is to make using cryptocurrency as simple and as safe as possible. And so for security, I'll show some slides. And for showing how simple it is, I'd like to show a couple demos. And I'll show one right now. It's my first time doing it live, so hopefully I have beginner's luck. So this is a software wallet, a popular software wallet called Electrum. And I wrote a simple little plugin to make it interface with the digital Bitbox. You can see the tab up here. And the main function you use with Bitcoin is to buy something or send your money somewhere. And so I'll just show a simple example how that is possible. And so just plug it into the USB port like this. I already have an address up there, so just send this person a couple bits. Hit send. Enter the password. This is a password on the device. And we get this QR code that pops up. So this is an optional second factor authentication. You can ignore it if you want and just continue. But if you want to use the second factor authentication, there is a very simple smartphone app that I made. It's available on the Android store right now. Looks like this. And you can use this to scan the code. And right now it's not true two-factor authentication, right now it's just a verification of what you're sending is really what you think you're sending. So it'll show, for example, I took this picture earlier, so it's different addresses, but it'll show the send to address and the amount. And I guess one person can take a look. Yeah. And so let's say something's wrong, something looks wrong, or you change your mind. You can touch the button briefly, like that. And this is to reject. Let's come back over here. Aborted by user. Could not sign the transaction. If you want to sign the transaction, let's just try it again. Enter the password. And let's say everything's okay. And then in order to sign the transaction, you just hold down for 3 seconds. And the transaction signed. And then you can just broadcast it so it's on the network and continue. I don't have internet connection right now, so I can't do that at the moment. Okay, so then to enable true two-factor authentication, just to explain a little bit further, let's see if I have, enter the address again. If we come over to this tab over here, it has a couple of options, configuration options. Focus on this part first, this verification password. And so this QR code, it's encrypted. It's encrypted with a key that's generated on the chip. And that key is shared with your smartphone app through the micro SD card. So this is also always offline from your host computer. So you can be confident that the QR code you see on here was not tampered with. And so in order to enable true two-factor authentication, what that means is not only does the phone display the information, but you actually need the phone to unlock the transaction to send it. And so that's done over here with just a simple command. So first of all, you can create a new key, export it to the micro SD card to load up here, which I've already done. And then if you hit this lock button, now it's locked. What that does is it disables the micro SD card, so nothing can come out of it anymore. Your wallet's frozen, so the addresses you have are now fixed, although it's a hierarchical deterministic wallet, so you can, from this fixed seed, you can generate any number of addresses. And if we go back to sending, you'll see what happens now. Again, there's a QR code, and this time we'll get one extra piece of information, which is this lock code. And this is a one-time password, one-time PIN, and you use this to unlock the signed transaction before it's being sent. So in this way, it requires possession of the smartphone also. Is that clear? No? So well, I'll just show the demo what happens next. So say everything's okay. Hold down the button, and then this window pops up. So enter the lock code from the phone, you enter it there, and then it unlocks it, and then you can send it. And let's say you enter the wrong code, and then it'll just stop, so you cannot sign the transaction. Yeah, so there's a port for a micro SD card. You just connect this to load up the secret key to unencrypt. And then I have this little device. It just plugs into the phone, and you can load it from the SD card onto the phone. Yeah, yeah, only that app. Yeah, you scan it, and then on the phone you see the lock code. You could have it with as many phones. You just have to load up the same verification key into different phones. If you use your phone, you can just create a new verification key, and then the old one is no longer valid. Yeah. So I guess when I send the transaction, I type in a password. Yeah. So I'll have some slides explaining it in a little bit more detail later. So maybe I'll get to that point, and then if it doesn't answer, ask me again. Okay, so this is the signing. That's it. And I'll show some more demos later with some other features. The mobile does not need internet connection. For the two-factor authentication, it does not need an internet connection. Of course, you need an internet connection to broadcast the signed transaction. Yeah, if, for example, if you're at a store that accepts Bitcoin. Yep. Okay, so in the rest of the talk, I'll go into a bit more detail about the basics, talk about the security threats and the defenses. Depending on time, I'll have some more demos, how to create a wallet and walk through the control panel, and talk about what's next. So I guess also I should say some things about myself. I'm actually by training a neuroscientist, and before that, I have a couple of degrees in mechanical engineering, and that's when I started programming. Actually started programming robots, autonomous robotics, how to control them. And I continued programming while being a neuroscientist, making data acquisitions to record neural activity and also lots and lots of data analysis. And I got interested in Bitcoin maybe 2 years ago when I saw an article, like, why is this monopoly money on the front page of this newspaper? And so I started reading about it, quite captivated by the technology behind it. Thought it was really fascinating. Bought some Bitcoin, bought some more until my wife got mad at me. Thought I could retire by now, but no, I need a job. So thought, okay, it'd be really nice to be involved in Bitcoin. So how can I do that? Maybe start a company and give myself a job. And so that's what I'm trying to do. That's why I'm here today. And I knew, for me personally, I have some technical background, but when I first started using Bitcoin, it was quite complex for me, and it took me a long time until I actually felt comfortable with it. So I think issues of security and issues of simplicity are important, and these S words you'll see on almost every Bitcoin website these days. And so there's a market for it, and decided to try to make something along those lines. And the approach I'm taking is a minimalist approach. The idea is do only what is necessary and do this well. What's necessary is to create and store private keys to create your wallet and sign transactions and messages. How to do this? Well, it's a hierarchical deterministic wallet, so it follows these Bitcoin standards. What that means is you generate, if you're not familiar, you generate a single seed, and from that seed you can derive the rest of your wallet. All the addresses to receive money and send money. Bitcoin itself uses the elliptical curve cryptography. There's encryption between the device and the computer. And it follows USB communication, human interface device. And so all of these letters and numbers, these are standards, well-established standards, well-adopted standards. And there's a couple more libraries you need to do this, but everything's governed by standards. And so if you really strip down and do only what is necessary, it's all standardized, and that means there's no inherent need to change the software on the device if you just do the basics. And this will eliminate a potential attack vector. Someone installing malicious firmware updates. And all the non-sensitive operations, everything else can be done on a PC, which is, of course, easy to update. And so to talk about the communication, has USB communication, so you'd plug it into your computer. All communication is encrypted. Human interface device, this is a class of USB devices such as a keyboard or a mouse. And what that means, but it doesn't have to be only that, it can be any generic device. And what that means is you don't need to have kernel level drivers installed. No root level drivers are needed. Plugs into the device like that. Have a touch button with a backlit LED for user confirmation. If we take a look under the hood, you can see the touch button at the bottom. It's just a piece of copper. It's a capacitive touch button, so when your finger comes close, it gets detected. Pretty standard technology. The LED is in the middle. And the SD card fits into the silver slot. So again, offline, anytime backups, secure backups. There's a single-purpose microcontroller dedicated to being a hardware wallet. And there's an additional high-security chip that's used to store the secrets. And this chip is has a number of physical mechanisms to be tamper-resistant. And the chip also additionally has a hardware random number generator. And so hardware random numbers generators are important because you need random numbers in order to create a wallet. So you can do this on chip with the hardware random number generator. It also follows industrial standards. Just in case there's a problem with the chip, I add additional entropy to the random numbers. If you don't trust it, you can also input your own random numbers, your own seed, and you can do that either through the micro SD card or through the USB interface. If we move on to talk about security, what are the threats? I have a list of threats. If you can see another one that I didn't think of, I'm happy to hear it. So if we look at the computer side, a common one, so these are just general threats, and then after this I'll talk about the solutions that we use to get around these threats. So on the computer itself, you could have malware installed that logs your keystrokes or records your screen captures or steals your files. Man-in-the-middle attack, that refers to, for example, there's communication between the computer and the chip. Man-in-the-middle attack could be malware that intercepts this communication and, for example, changes the send-to address with an address controlled by the thief. If someone has possession of the device, they could try to brute force attack the password, try to guess the password. They could try to read secrets from side channels. I'll explain this in another slide. Glitches to bypass password checks, I'll explain this also. If they go a bit more invasive, there's techniques to actually strip off the packaging and read the bits on the chip itself, so physically reading memory, and of course malicious firmware. So we'll start with the easy ones to solve. So brute force password guessing. If you try to access the device 5 times and you're not successful, then it automatically resets and erases the secrets. And so if you do this by accident, if you have a backup, it's simple to just regenerate your wallet through the backup, through the micro SD card. Key logging, this is a problem mainly for software wallets. So it's possible to take the password that interfaces, that does the encryption between the hardware wallet and the computer. But even if the thief has that, they don't have the private key, so they can't do anything with it unless they also get your hardware wallet. And of course, if you enable second factor authentication, they also need your smartphone. Man-in-the-middle attacks. So like I said, they can replace the address you think you're using with a different address belonging to the thief. So the smartphone app, as I showed before, allows you to verify that what you think you're signing is really what actually is being signed. And furthermore, the touch button, it prevents remote access. So someone can't just do things while you're not looking on your computer and try to use the device. So reading secrets from side channels. So side channels, what that means is recording information from the device from unintended sources. For example, this could be the power fluctuations that the device, from the supply to the device. Or it could be electromagnetic radiation emitted by the device. It could even be sound from the device, because chips will have little vibrations as it's operating. And from these, this is just an example with the RSA algorithm. If you plot the power, for example, that you record, and in this particular cryptographic operation, the zeros and ones of the secret key are used to encrypt. And depending on whether or not it's a 0 or 1, you'll get a different computation. In this case, it's you do a square or you do a multiplication, depending on the 0 or 1. And just looking at fluctuations in the power, you can identify when a 0 happened or when a 1 happened, just from the power. And it's similar for the sound or the electromagnetic radiation. And thankfully, people are aware of this, and there's algorithms that exist, libraries that exist that make side channel attacks very difficult. So Digital Bitbox is using one such library called microECC that was designed to prevent known side channel attacks. And in general, what you need to do is make the computational times and the computational power equal, so it's hard to distinguish between the different aspects. Shorten the overall computational time, so it's harder to tell the differences, and introduce noise or randomness. And in naive implementations of the Bitcoin curve, the elliptical curve, it's been shown, I have a video I could show later after the talk, that even with one signing, someone can extract the secret key. Move on to glitches. So side channels is recording information from the device that was unintended. Glitches is the opposite. It's sending in some information to the device that's not intended by design. For example, you could mess with the clock line or send in voltage pulses. These are called glitches. A more general word is fault injection. And so if this is a clock line that the chip is using to process its instructions, the orange arrows indicate when a new instruction happens. And this is the general idea of introducing a glitch. You just mess with this clock line, for example, this blue area, and you could get a couple of different effects. One desired effect is just to simply skip an instruction. So you get this blue pulse and then the next orange pulse, and then the instruction that would happen at the blue pulse gets skipped. Another method is to degrade or corrupt the data that's being processed. And this depends on getting this glitch precisely timed and the right width. And just to show an example, for example, checking passwords. If you introduce a glitch here where you send the password and it's being compared to the correct password, you could skip this conditional loop and go directly to run the code. Or, like I said before, the Digital Bitbox, you can access it 5 times before it resets. So you could also put a glitch here where the countdown is, and then you avoid counting down to 0 until it actually gets reset. So this is the general idea, but in practice, glitching is a bit more difficult. I'll explain in a second, but first of all, even if you do a successful glitch, the result is harmless because in the Digital Bitbox, it's not actually checking for a password. All the communication is encrypted. So what it's checking is whether or not the command you send it can be decrypted. And so, of course, if you send a command you don't know the encryption, it gets past the password check. It's just garbage. Nothing happens. It won't be recognized and the program will exit. Furthermore, well, okay, so we can't bypass the password check, but we could bypass the countdown. However, which is the second point. However, in order to do that, first you need to access these clock lines so you know where you are in the program execution. That's invasive. It means you have to rip through the package itself and dig through the epoxy, so it'll leave noticeable traces. Furthermore, glitching itself has low odds of success. This paper I referenced, they had it's an academic lab where they had an ideal situation with a simple chip. They knew everything about the chip, everything inside of the chip, everything about the code that they're using, and they're only able to have success 50% of the time. And in practice, success is usually much lower than that. And so that means, say you get 50% of the time success with the digital Bitbox, then you could have 10 trials until it gets reset. So that's still not enough to do brute force password attacks. And furthermore, there's some code redundancy in the digital Bitbox where 2 precisely timed glitches are required in order to skip this countdown, which of course makes it more and more difficult. And there's just some more technical details of why this is difficult, but I'll skip that for now. And move on to physically reading memory. This is another interesting attack. This is the general process. You take a chip and you etch away the surface of the chip. In this case, they use a chemical to etch away the packaging. You could also use ion beams to evaporate layers, or milling to mill down. And once you have the chip exposed, you can view it with a microscope or a scanning electron microscope. And this is an example of what you could see. This is actually a very old ROM chip from an arcade game. And you can see the little dots around here. And what these represent are little solder joints between different layers of the board. And where you have a dot, that's a 1. And where there's not a dot, it's a 0. And if you apply some machine vision algorithms, you can extract this automatically and basically just read what the memory is. So again, that's the mechanism in general, but in practice it's more difficult to do. It requires rather expensive equipment. For example, modern chips will have the circuitry in different layers, so you need to not only remove the packaging, but you need to remove the layers of the chip die itself, and that takes very expensive equipment. Ion beams to very precisely etch away the layers, but it's still possible. Just takes a lot of knowledge, a lot of smarts, a lot of time, a lot of money. And furthermore, with the digital Bitbox, we use this high security chip, which is designed in particular to have physical security features to make it difficult to do this process. It's just a paragraph from the user manual. And furthermore, let's say you could actually read the bits. The secrets are encrypted twice, actually, on the device. So not only will they need to read the bits, they'll also need to decrypt it. And it's encrypted once in hardware with the internal memory encryption, and also one time in the software code. So, yes? Yeah. Yep.
We also need this for this to work. The
Yep.
SD card. But is the SD card itself designed for this security?
Yeah. Most of them, no. Ones you buy in the store, no. So the SD card, and there's another thing to mention about SD cards. They have a limited lifespan before the memory goes away also. So the SD card is intended as a short-term storage. Short-term meaning few years in time. And the idea would be you either renew the backup or you put the backup into something that's very long-lasting. Etch it into stone or metal, or create another paper wallet, for example. Yeah. Yeah. Yep. Yep. Yeah. Yeah. So it's a very good question. Yeah, it's the same issue for any type of cold storage. How do you keep the cold storage safe? If you have a SD card, you probably want to keep it in a safe. If you have a lot of money, you probably want to put it onto more permanent media, either paper or metal, for example. There's some solutions where you can have metal-based cold wallets. Yes, that's a great idea. Yeah, yeah. So, yeah, yeah. Stick the other one in a bank vault, for example.
Sorry. In normal usage, do you need the SD card in the device, or is that really just for the backup?
So it's only for backup, and it's also for, I think it's recording into the video. Yeah. So it's just for backup, or for the second factor authentication. So passing the second factor key to the smartphone, for example. But it's not required for operation.
And it doesn't hold any data in that sense?
No, it only hold, if you make the backup, then it would hold the backup seed. But that's it. Yeah.
So, I mean, in theory, there's a secondary market for accessories. Like you sell like a tamper-resistant SD card, or
Yeah.
something.
I believe there's actually a company in Switzerland making these devices already.
Okay, interesting. I'm not jumping around too much, but let's say the person who's using the Bitbox does not make a backup.
Yep.
And they lose or destroy the Bitbox.
Yep.
What is the recovery protocol?
It's gone. Okay. Yeah, the Bitcoins are gone. Okay. So move on to the firmware. The so-called evil maid attack. So if the maid is in your hotel room, she's by herself with your Bitbox and laptop, she could try to update firmware. Probably a more realistic scenario is if there's a rogue developer who pushes a malicious update, an official update with something hidden in it. These are possibilities. Just as an analogy, if you look at the failures with the online wallets for the exchanges, for example, Mt. Gox, I got a letter today from the bankruptcy trustee, bankruptcy claims. So these types of jobs are considered to be inside jobs. Most people think someone inside had access to these private keys and were able to steal millions and millions of dollars worth of Bitcoin. So the exchanges are centralized. Hardware wallets, of course, are decentralized. But if you allow firmware updates, that's basically another way to have a centralized access point. And if a hardware wallet gets adopted, there will be a lot of incentive for someone to try to infiltrate and malicious updates. With the digital Bitbox, firmware updates are not possible. Also, the debug interfaces, the pins are disabled. You can't use them. And for this Bitbox, but also for other hardware wallets, multi-sig, a great option. And I'd highly recommend that to be incorporated in the future. Right now, the digital Bitbox, it allows this, but we need to write some interfaces with software clients to actually start to use it. Yeah, yeah, yeah. When we get time to work on it. So, yeah, so the man-in-the-middle attack will also be prevented by multisig. But the issue here is how do you make yourself safe against something wrong with the firmware itself on the chip? And so if you have a multi-signature somewhere else that's not dependent on the hardware wallet, then you can have additional safety. So maybe the best security is actually get 2 different hardware wallets by 2 different vendors. Put one SIG on one hardware wallet and a different SIG on another hardware wallet. Yeah. Okay. So the goal is to make it impossible for thieves to steal your coins. But is that really possible? Is there a way to steal coins? It's important to mention that if a human can make some device, some hardware wallet, then another human can come along and be smarter and figure out a way to hack it. And the idea is just to make this extremely difficult, and if it's possible, to make it expensive and time-consuming. So some basic ways that people could steal your wallet, the obvious ways, if they have your device and your password. If they don't have that, they could steal your backup. If it's not encrypted, there's an encryption option on the backup. Or the expensive and difficult way, steal your device and do invasive probing. And also, there's no firmware updates, but how do you trust the initial firmware that's on the device? I don't have a good answer for this. I'd be happy if someone does have an answer. For example, one way you could allow users to install the firmware themselves, but you could have a second circuit on the chip itself that communicates with the USB that doesn't get updated by the user. So how to do this in a way where with 100% reliability is a tricky question. It's open source, yes. Yeah, so that's possible, but then again, you could have a different section of the code looking for whenever you check this hash, and then it will give you the right answer, whereas a different part of the code can be operating independently of that. So I think it's a tricky issue. And so again, I think probably the way right now, the practical way to get around it is again using a multi-signature approach. How are we doing for time? $20 more minutes? Okay, so I'll just show a couple more quick demos, and then only a few more slides until it's over. I'll come back over here. So we have this tab over here. So I'll plug it back in. We can do different things. For example, the random number generator. You can access the random numbers and see that they're changing. to verify that the random number generator is working all right. Toggle the LED, for example, change the password, erase the device, and rename the device, for example. Some options for the SD card. Let's see. Plug in an SD card. List the files on the device. Oops, the device is locked. The SD card is disabled. So I'll get to that in a second. And then, as I explained before, the create and export and lock. And so, okay, let's say you want to start over, or you want to erase your device so you can sell it to someone else on the second market. You hit this erase button. It'll give you a warning. Do you really want to do this? It says push the button 3 times in order to erase. And it's erasing the device, and now it's erased. And so we have a blank device. If I try to list the files, it'll say, please set a password. Let's just close this and just open up a second wallet. And I'll show you how to regenerate a wallet, how to create a wallet. So we'll just create a new wallet, hardware wallet. We'll use the onboard random number generator. Hit next, digital Bitbox. It's an optional passphrase. I'll just leave it blank for now. Enter the password. And now it's generating the seed. And soon it'll start communicating with the software wallet and loading up the addresses. And we're offline. But you can see the addresses here, so you have a wallet ready to use. Sorry? The addresses? So it's a hierarchical deterministic wallet, which means you can derive almost infinitely many addresses from one seed.
Yeah, thank you. But I understood that most wallets do like a reserve allocation of a couple of keys. That, because even though you can redetermine it, you need to know how many to redetermine or which ones, right? So let's say you do 100, and once you run out of 100, probably you need to at least then a backup again, right?
Yeah. So this situation is just governed by the software wallet itself. So the software wallet can ask for more addresses from the hardware wallet. Whenever it needs more addresses, it can just ask for more addresses, and they'll be generated. So you won't run out of addresses. Nope, because it's all the addresses are generated from a single seed. So it's kind of like a tree. You plant a seed, then you have a lot of different branches coming out, and each branch is a different address. And so from the same seed, you can follow the path to different addresses. Okay. I can explain more later also. Okay. At the moment, yes. Yeah. Oh, yeah, definitely. So also part of the motivation to make it minimal is also to make the API very simple, so that it's easy for other software wallet developers to incorporate the digital Bitbox. Because of course we don't have time to make an interface for everyone. I will try to make interfaces for maybe a smartphone-based wallet, a JavaScript wallet, to have a different option. But yeah, this needs to be worked out. Okay, so just one more example. Let's make a third wallet. So note erase the digital Bitbox. So if you already have a device and you go to a new computer, you buy a new computer, you can generate or you can connect to your software wallet with the existing hardware wallet. So restore. And import an existing wallet on the device into Electrum. There's other options where you can create a new wallet by entering a seed in Electrum, so through the USB port, or you can load your backup wallet. So let's do the first option. Enter the device password. And again, it's going through the same process of loading up the addresses into Electrum. Offline. And again, you have the addresses. So that's for creating it, creating a wallet. We'll go over here. I'll show you one more thing. Oops. Okay. So this is, you mentioned other interfaces. So this, it's not a wallet, but it's an API interface written in JavaScript. It's a Chrome application. And this is just another basically configuration box. So you can do the same things as before. It opens up the whole API. So for example, you can get the device serial number, the version, xpub. This is where if you want to generate a new wallet, you can enter the path, which is governed by these Bitcoin protocols. And it'll spit out the public key. So this is how to get a new address. Erase, lock it, list the files. Let's see if we can do this now. So verification text. This is the verification file I uploaded before. You can erase the files. Do a backup. You can unencrypt or encrypt it. I'll just cancel for now. Get random numbers, genders, random numbers again. And then there's one more feature I'll talk about, which is AES encryption. So the AES hardware module on the device is also accessible through the API. So you could use this as a hardware-based AES encryptor. And to do that, just enter a key, 9999. So that's the password. Hello, Meetup. We'll encrypt this. Spits out the encrypted text in base 64 notation. Enter it. You can decrypt it and get your message. So you can share secrets with other people. Okay. I can show, after the talk, if you're interested, I can show more features. So what's next? Get your feedback. I'm very happy to hear feedback either after the talk or by email or through our GitHub page. I'm in the middle of a security code audit to make sure the code on the device is also very secure and reliable. Again, work with software wallet to provide simple user interfaces. And finishing touches. Lots of finishing touches. So, in summary, like other hardware wallets, the digital Bitbox is a single-purpose microcontroller. Communicates with USB. It's open source. It has some additional features, such as no firmware updates, a strong and durable case, two-factor authentication option, this encrypted communication that's immune to glitching, private keys isolated on this high-security chip, resistant to physical tampering, offline anytime backup with the micro SD card, and a side-channel resistant open-source elliptical curve library. And again, our goal. With that, thank you very much for attending, and I'm happy to answer questions and talk more tonight, over beer even. Should be nice. Thank you.
I have a question about connecting a software wallet. If I have more sophisticated software wallet, like an e-banking approach with multiple accounts, and I have to perform multiple transactions at one time, it's mandatory that I push the button every time, or can this bridged somehow for such a case, or via a modified firmware?
Yeah. So right now you have to touch the button every time. But if there's a different use case, it's relatively simple to change the code or change the hardware itself for banking applications, for example, to handle this. Or there's also some ideas of maybe having an industrial version, for example, on Bitcoin exchanges, in which case you wouldn't want to touch the button all the time, but it'd still provide security for holding the private keys.
Okay, thank you.
So do you plan to open up the other, not necessarily only Bitcoin?
Yeah, so right now it's actually out of the box altcoin friendly. So any altcoin that uses the same signing curve as Bitcoin will work with this wallet. Again, you have to make the correct software interface.
Ether or this kind of different altcoins, but different coins, like from Ether. There are different ones.
I see. Yeah, I'm not familiar with the technical details of these, so I'd have to research it. But basically, anything that uses the SECP 256K curve would work with this.
Great.
Any more questions? Okay, we can continue the conversation over beer. So, thank you again.